So that was just kind of a review from the transmitter nonlinearity, and all of it applies in general to the receiver because it's general for all nonlinear systems. So the question is, at which stage of the communication system we suffer most from gain compression? At the final stages of the transmitter when the signal level is increased by the power amplifier. And so the question is, if the transmitter is the area where we've seen gain compression the most, can the receiver performance also be affected by nonlinearities, and how? So we focused on gain compression in the transmitter because it's one of the dominant nonlinearities in the whole system, but can we find it in the receiver? So has it ever happened to you that you could not hear a low sound when others were speaking loudly next to you? At the input of the receiver, a strong interferer may exist close to the desired signal. So here's what we transmit. Here is the cell phone tower right next to us, or it may be a radio that's right next to you. And your receiver is going to receive both of these signals. And so let's look at intermodulation when we receive two signals. So here's an example of our first signal and our second signal. And this math should all be familiar to you just from the nonlinearity slides that we've done before. But we can see that as before, we end up with all of these tones that are the sum and differences of the two frequencies, and that they're dependent upon the amplitudes of both of these. And here's a typical spectrum of each one of these. And indeed, if you were to put this into a nonlinear amplifier and measure it on the spectrum analyzer, you would see exactly this. So let's go back to this thought of desensitization. For simplicity, for the analysis, we'll approximate the two signals with just single tone sinusoids. So that makes everything simple. And so we are going to take our nonlinear gain here, and we're going to assume that A1 squared is small, and that assumption comes because our desired signal is small. So we're assuming that A2, if you will, this is A2, are related to A2, and this is A1. Okay? And so we simplify our gain to just be this. And since alpha 1 and alpha 3 are generally less than 0, the receiver may not sufficiently amplify the small A1 due to the strong A2. So let's put in our signal here, and if we look at our output gain here, we may not actually get A1 amplified because A2 is so much larger. So what we're going to get is simply alpha 1 and then a nonlinear gain to alpha due to A2. Any amplitude variation in the strong interferer will also appear on the amplitude signal of the desired frequency and distorts the signal. So here's our desired signal, here's our interferer, and if you look at what comes out at our fundamental frequency, look at that. A2 is now modulating our desired signal because of its intermodulation product. So I'm just going to back up here so we can see that again. We see that our gain has a fixed amount and then also this nonlinear amount that's due to A2. Now it does have a nonlinearity due to the amplitude of A1, but because this is small, we're dominated by A2. If it wasn't small, we would just include this A1 here, and we would have a nonlinearity, but it would be the signal modulating itself, and that's not necessarily a good thing. But what's happening in this case is that the nearby interferer is modulating directly our signal. So in the previous one, we talked about interferers, but we also remember that even if we have two desired tones, we get intermodulation products that can be harmful to us. And multiple tones may be, for instance, different in-band channels at the same input of the receive, LO and RF signals. But intermodulation is not always a bad thing. So up to now, we've made it sound like this horrible thing that we've had this nonlinearity and we have to fix it with a bandpass filter and be very careful. But not always. In fact, every radio system uses a specific nonlinearity to achieve one of the most fundamental functions, and that is the mixer. So multiplication is generally, until we had digital radios, it was almost exclusively not done mathematically, but rather using a nonlinear transfer function. If you remember, the Taylor series of a nonlinear transfer function has a squared component. And if we set the input to that nonlinear system as the sum of our LO and our RF signal, it will multiply them for us.